Hey everybody, welcome back to Tech Junior Tutorials. My name is Lee Warwick Jr. and we're doing Advent of Code. Today is actually day 17, I believe. I've kind of lost track. I'm on vacation. I've been doing a lot of stuff over the holidays, so haven't been able to follow Advent of Code that closely. But we're going to be talking about day 15 today. So let's jump on over to that problem. So you can see today's day 17. I'm still working on 16. 16.2 or part 2 is pretty rough. So still working on that one. Although the part 1 you could get with a brute force solution, I think, right off the bat. But we're going to talk about 15. So let's take a look at that one. So this one, again, we're back to int code. We won't go over that too much because there's a lot of other code to cover. But today is oxygen system, and basically what we're doing is navigating a maze. So they say your robot, or you're supposed to make a robot to find an oxygen tank somewhere in the ship because it has to go repair that tank. So it's going to run on int code, and int code is always going to take an input and an output command. So it says the input is going to be a movement command from you, and then the output is going to be the status of whatever the thing you bumped into is. So they say you've got 4 directions, north, south, west, and east, 1, 2, 3, 4. Anything else is invalid. Anything else will halt in code. And then your output codes are 0, meaning you hit a wall. So your position has not changed. 1, meaning that you've moved successfully. And your new position is the position after moving 1 space in that direction. And then 2 means you found the tank, and you did move. So they give you a little chart here, which is kind of cool. So they're like, okay, if you try to go up, position doesn't change, but you now have hit a wall. If you go east, you'll move, and then that'll be like your previous position. Here it's showing you like in a dead end, and then basically it kind of shows a little bit of this map. So for my solution, we'll just jump right into it. I again have the same stuff as like day 9 and the previous int code solutions. I have my same int code computer with its helper function get inputs. And then I've got the same command to read from the file. So here's the input for this day, just a big string of comma-separated numbers. And then from there, I start out and I say like, okay, I need some global variables. So for this one, I want to keep track of all the positions that are walls, all the paths that I've traveled over, all the dead end paths, or all points that end up in a dead end. And then my current position, my next position, my previous position. There's a lot of globals that I'm keeping track of. The tank location, if I've found the tank or not. And then what happened after I tried to send an input. So like that's that 0, 1, or 2. Did I hit a wall? Did I move? Or did I find the tank? So whenever I did this first, I did manual inputs. So I gave it like a 1, 2, 3, or 4. And to figure out like what the maze kind of looked like, I went ahead and visualized it. So I wrote this, it's kind of massive. So I wrote this massive print grid function, where first what I do is I find out the minimum and maximum X and Y values. So like how far left and right I've gone and how far up and down. And then, so I loop over the values that I store in paths and walls. So paths and walls are going to be, how big my grid is. So I never move past a wall or a path. So as long as I stay within those ranges, my grid should be enough of a size. So from there, I get the width of the grid and the height of the grid. So I just take like my max x plus my max, or my min x plus 1. Same thing for y. And then I do some list comprehension here where I just make a big grid of spaces, basically. So a bunch of rows of spaces, and then the y value is another list of those rows. From there, I do some math to convert any given position, because the way that I'm tracking this is if I go up, I'm going to say I have a y value of -1 or a y change of -1. So if I'm at 0, 0, and if I go up, my new position will be 0, -1. If I go down, it would be 0, 1, so on and so forth. So in order to convert that into a zero-based coordinate system, like what my grid is, so in the grid, top left is 0, 0. So I need to find out, like, if I'm at, let's say, 0, 0 on the maze, that's not necessarily going to be what 0, 0 is in my grid. So I need to convert those numbers. So I've got kind of a messy formula to do that, but basically I say, like, for any given position that I'm at, the x value, if it's less than 0, is going to be the absolute value of the minimum minus the absolute value of x. If it's greater than 0, it's going to be the absolute value of the minimum x value plus x. And otherwise it's 0, so I'm going to take the absolute value of the minimum. So basically, like, I went to the left and I was at -1, 0, my minimum value would be 1, or -1. So my x would be 1, because my grid is going to start at 0 at the top left. So 0, 0x, 0y. Really hard to think about. Believe me, I had to debug this a little bit and get the numbers, like, just perfect. But basically from that point, I grab each position in the walls and the paths, which I'm storing as string values, so that they're just pipe separated, so like 0, pipe 0. So if you look up, well, in the second solution, you can see, like, this is how I'm storing my values, but we'll get to part 2. So every position in walls, dead ends, paths is going to be that pipe separated string. So I convert that with a helper function here. So just split based on the pipe and then return 2 numbers in a tuple. So for that, I grab each point, convert it, and then in my grid, I say, like, a wall is going to be a hashtag, and a path that I'm on is going to be a period. Anything else will be a space. And that is going to be like dead ends and unexplored space and all that good stuff. From there, I get my bot's position, and that is going to be the @ symbol. And then I'm going to say, if I have a tank location, go ahead and make that X, for X marks the spot. Clear my screen or my terminal using this little Stack Overflow code that I found. And then for each row in the grid, I'm going to join on a space and then print that row. So we'll see the output of that in a second, but let's look at my manual input code and my outputter code. So for outputter, this is values coming back from int code saying, like, this is what you found. I'm looking at tank location, previous move result, and tank found in the global scope, which is kind of funky in Python. I'm really not used to that coming from JavaScript. But essentially, if the code's 0, that means I hit a wall. Go ahead and add that location to the walls set. And I've got, again, another helper method for that, or helper function, that just takes the chords and turns them into a string. If I've reached code 1 or 2, that means that I've moved. So go ahead and make the result moved. And then make a point. And then if that point is not in the dead ends, add it to the paths, which I had to come back and refactor that a little bit because originally I didn't keep track of dead ends. But so I add that point to the path, and then I go ahead and save that previous position based on my current position, and then I make my current position what would be the next position, because it told me that I did move, so I need to update my current position. And then for code 2, that means I found the tank. I flip a flag in the global scope that's like, yep, tank found, and here's the position. So not a whole lot of complexity there for the base outputter. And I think I use that same code for both the manual and the automated input. So for manual input, this is really simple. I just say like, here's my current position. I ask for input, and I use WASD to move up, down, left, right, just like you'd use for your favorite video game. And then if it's not 1, 2, 3, or 4, like if I didn't type in WASD because sometimes I fat finger it and type it twice, I just call this again. And then I convert, actually I grab those next positions. So like I'm trying to move is basically next position. So like if I'm going up, that means X is going to be -1 from where I'm currently at. If I'm going down, it'll be 1 more than where I'm currently at, so on and so forth. So the coordinate math and stuff is something that is really hard to reason about when you're a beginner. But the more and more that I do this kind of stuff in code, the easier it gets, as long as you're thinking about top left being 0, 0. So basically after that, I'm returning the value 1, 2, 3, or 4. And then I just plug those into int code. So if we do that, you'll see I've got my inputs, which is that input string up here. And then I've got my manual input function and my outputter function. And we'll get to this bot function in a second. So if we run that, you'll see I've got a blank right here. But if I try and go up, you'll see like up, that's a wall, down is a wall, right is a wall. And you can see I'm actually moving around this maze. So this is like a human-controlled maze robot. You can see like sometimes I hit the wrong key or hit it twice or something. So you can see like this is a pretty big maze. It would take you quite a while to get the solution this way, even with the WASD controls. So notice like my grid is resizing as I go further and further north, or further negative. That's why I'm doing all that fancy math to find that. So basically whenever I was playing with this, I was kind of like, man, I want to know not just like what path I'm looking at, but I want to know where all the walls are. So like as I'm going, I want to probe in the other directions and see like, I want to fill out this map basically. And you don't have to do that, I don't think, for the solution. But because I wanted to visualize it and make it look like really pretty, I ended up wanting to keep track of that anyway. So instead of just like cutting a straight path, like every time I move, I want to check up and I want to check down, and then up and down, and then if I'm going down, left and right, so that I get a like really clear picture of what that path looks like. So I know kind of what the maze structure is. And so for my algorithm that I did, that's kind of what I prioritized. I originally thought of doing like a right-hand search, which is something that firefighters do. So if you're in a building and you can't see, you keep your hand on the right wall, and then while you're touching the wall, like reach out and search the area that you can reach from the wall. But being a former fireman myself, I know like the peril of that is that you may miss stuff if you don't ever let go of that right wall. And so looking at the puzzle input and actually visualizing the maze, you can see that there's some nice things going on here. First, everything in this maze, the path is only 1 unit wide. So there's only enough space to go in one direction unless you hit a fork. which there's one in here somewhere. I think this is it. So like right there, there's a fork in the path. So you can see like if I go north, I'm in a dead end. And we can probably blow that up a little bit. If I go north, I'm in a dead end. So what I was worried about doing, just like a right-hand algorithm, was that if I end up in a spot where there's a big empty space, like if I'm in a room or something instead of just a hallway, I may not, like if the tank's in the middle of that, you'll never find it if you don't come off that. But visualizing this, I could see like, okay, basically that's never going to happen. Everything is a hallway, basically. And then from there, I was worried like, well, what happens if I hit a four-way intersection? It didn't seem to be the case looking at it. It looked like there was only three-way intersections, so the way I'm coming from, and then like a choice of two different paths I could go. So that simplified the inputs a little, or the algorithm a little bit, but it was still like quite a bit of programming and math to get this. So let's go ahead and check out what that took. So I didn't use the manual input. I've got like a bot that has its own input function. So if we look at the bot, that has its own craziness going along with it. So it's got some different methods in it. It also has its own state that it's keeping track of. So I originally had like just a general state for the bot, but really I found out that I only really care about its searching functions state. So I just called this probe state. And then its probing location is the spot where I'm looking from, because I'm actually, if you watched when I was manually moving, I would move like forward and then back and then check the walls. So like the position I was getting my surroundings from, that needed to stay the same even though I was moving in different directions. So I had to keep track of that position here. And then from there, I've got a helper function to explore or at least get some information about the four positions around any given position I was in. So I look at the global position, create a dictionary for all of these different points that I could allocate positions around me into. So it could be a path that I've already walked, it could be a wall, it could be an unexplored spot, or it could be at a dead end, like a known dead end on wherever I'm at. And then from there, like I calculate what would the coordinate be if I went up, and that would be x and then y minus 1. Do that for all the directions, store that in that dictionary, and then I loop over those directions, and then I get a string. So like how I'm storing those points in those sets, paths, walls, dead ends, and whatnot. And then I check to see if any of those coordinates is in those sets, and then put that in the respective list, and then just return that dictionary. So every position that I move to, I call this function and say like, hey, what's my surroundings? From there, then I've got a probe function, which is where all this complicated state lives. So thankfully, I moved away a little while ago from using Booleans for all of my state and trying to explicitly describe like what am I doing at any given point. So I do have a little bit of implicit state, which I could have called this initial, but I say like, hey, if there is no global or class probe state, if it's none, which is what I start out at, so that's kind of initial, then I want to say like, okay, from here, I'm going to save the point I'm at, and then if I have a previous position, go ahead and store that as well. And then I'm going to change the state to probing surroundings. And then from there, I jump into this big switch or logic block. I say like, okay, if I'm doing if I'm in a probing state, if I'm not at the starting location, just go ahead and go back. So in my get move code way down here, I store some extra stuff from the manual input. So yes, I'm still doing the outputted direction of 1, 2, 3, or 4. It still returns that at the end. But now it's going to take in a direction to go in. So I'm going to call the probe function, and that's going to return up, down, left, or right. And then that is going to fall into this if-else block. And then I still store my next position and my output direction. But now I pick up, like, here's the direction I'm intending to go, and here's the direction that's opposite of that, in case I want to return to where I'm at. I don't actually think that I use this anywhere. I only use the direction to go back, but I figured I would save it anyway when I was coding it, just in case. So back up to where we were. If I'm not at the start location, go ahead and go back. If I'm at the start location and there's more than one unexplored direction, like, go that way and see what's there. Otherwise, I've explored everything. And if there's two paths, meaning like there's behind me and then there's in front of me, go ahead and look for whatever path is in those paths. So those two possible directions, loop through them. And then if one of those is not the last location that I was in, go ahead and go that way. So basically, if I came from south and then I moved north, and my only possible new direction to go is north, go ahead and go north. If there's more than two paths, that means I've reached a fork in the road. So I go ahead and I reset that state to none, which means it's going to start looking again. And then I save the fork location. And then I save, so I'm not even sure if I use that fork location, but I save the point that I was at before I reached the fork. And then I basically just choose an arbitrary direction. And then once I do that, because I've explored like that T, I don't know if I can show it to you. Like, okay, so if I'm here, let's say the @ symbol is there. I want to choose at random. Well, it doesn't really matter, but choose one of either up or down. If I go up, I don't want to store that in my path. I want to forget about that point, because once I go up and I hit a dead end, I want to turn around basically and come back to the location that I was at, and then mark each spot as I go as a point in dead ends. So it will kind of like erase that path and consider it a dead end. So, and this is a lot of code, so this could probably be like coded a lot better, but this is what I finally landed on. So I loop through twice, and the first time I grab my chosen direction, and then I loop through again and say like, hey, if it's not my chosen direction and it's not the path I just came from, go ahead and remove that from paths. So again, that would remove, since I've gone this way, that would remove that point. And then, so that's all if I've got a fork. Otherwise, if I don't have two paths I can go in, I'm not at a fork in the road, that means that I'm probably at an intersection where I've got three walls around me. So I say like, hey, if I'm at a spot where I'm at three walls, and that spot is not 0, 0 or the origin, you've hit a dead end. So remove that from path, add that position to the dead ends, set my state to backtracking, and return the opposite direction. Otherwise, I'm going to, like, if I am at the origin, like, go ahead and set me back to none, and then basically move in whatever direction there is that's left. So if I'm at the origin, remember, like, that's here, right? So in this spot, there's only one way to go, and if I'm at that dead end, like, I started a dead end basically, so I don't want to be stuck in an endless loop. So I kick myself out of that state by just setting the state back to none and moving myself in that one direction that's left, and then saying like, okay, start exploring again. So from there, whenever I hit a dead end that's not the origin, I'm I'm going to say if I've got no other explored points, or no unexplored points, keep removing those paths and add it to dead ends, and return the path that's left. So like each calculation, I'm removing my previous position from the possible positions by adding it to the dead end and removing it from paths. So every time that I backtrack, I only have one correct direction to go. Then if I finally hit that unexplored spot, so remember when I started down this hallway, I removed this. So when I finally come back, I'll have a dead end where I've been before and a new location to explore. I reset it again. So I'd say like, okay, I'm back to looking around. Go ahead and return that one unexplored direction. And that is it. So once it does all of that stuff, I've got actually at the very top of this function, it's just going to loop that and keep exploring until it hits the tank. So once it does find the tank, then it prints the location and it looks at the length of the path. So it doesn't count that origin spot because I didn't go anywhere. That's where I started. So the length of all the dots basically minus that original location. And that's the steps it takes to get there. So if you run this, it's actually pretty cool. Well, let's do that big. So here we go. You can see it's exploring. It's a dead end, removes that. So you can see it removes the space. Keeps going. Whoop, I've actually run out of space. Ooh, there. Okay, so you can see like it started here. It ran all through this, this way. It's a dead end, removes it. Keeps going, hits a dead end. So it either will explore the dead end and count it as a dead end, or it'll just ignore it and start exploring the other direction. So, like here, this space is totally unexplored. It didn't even check to see what was there, I think. Same with up here. Like there's way more maze up here, but because it picks a direction at random, like it just finds the tank eventually. So down here at the bottom, we have the tank position of -12, 12, -12, -12, and it took me 212 steps to get there. So if you counted all the dots on the screen, that would be 212, even though it doesn't look like it. And if we look at the puzzle input, that is the answer. So that was a really cool way to get the answer. I really like this problem. Part 2 is another interesting one. So here they're going to ask you, all right, now you turn on the oxygen at that tank location. How long does it take to fill basically what is the entire maze with oxygen? So it's going to say like, if your tank is here, you turn it on, each minute that passes, it's going to like grow outward in any given direction. So like it's got 2 available spaces next to it. It goes and fills those. And then from there, it's got 2 more. That one and that one. So it fills those, and then, yep, next it's going to fill that one and that one, until finally it fills that one. And then the whole maze, in this tiny maze, would be filled with oxygen. And it took 4 minutes. So where does the 4 come from? You start there. It takes 1, 2, 3 minutes to get there. 1, 2, 3, 4 minutes to get there. So they're saying that the answer is 4 minutes. So what I took this to mean was that you could do this 2 different ways. You could spawn multiple like pathfinding functions or classes or whatever that would each go in a separate direction at the same time and basically find each dead end in the map. But what my algorithm does from the start is it will go and find each dead end already and then mark it as a dead end. So basically what that means is if mine didn't find the tank, it should explore the entire graph. So if you look at this and I remove this code and I run this again, it's going to take a lot longer this time, but you'll see that eventually it's going to hit where that tank was, which was up in the top left somewhere, and it's just going to keep going. So keep going, keep going, keep going. I believe the tank is right there, and see it skip that. So now it's going to keep exploring the maze. So I've already got an algorithm that finds basically everything in the maze. The next thing is basically to find all the dead ends, which I've already coded for, right? Because I know when I need to turn around. Here, my terminal is not big enough, sorry. So when I hit a dead end, I need to know when I hit 3 walls, so I can turn around, go the opposite direction. So I've got kind of the key pieces already to solve this. Basically from there, instead of doing multiple pathfinding bots or whatever, I know that I can find the longest distance from the tank to the dead end, and that should give me the time to fill the total area, because anything shorter or equal to that is going to take either the same or a less amount of time. So I need to find basically what is the longest path from X to any given dead end. So from X to the furthest dead end is going to be the minutes it takes to fill this maze with oxygen. You can see this thing is still running, so let's go ahead and kill that for now. But you can see this is what the maze looks like for the most part. We have to map the whole thing out for the next one, so we'll hold off there. So for my next solution here, I only had to make a couple changes. So first, I store the origin as a string and a global variable. Next, I'm going to, all this other, like the helper functions and everything, those are all the same. Outputters, the exact same. Mazebot, for the most part, is the same, except for the probe function. So I've added a little bit to the probe function. Basically, I'm now going to look at all these global variables. So I need to know about dead ends and the greatest path length, which I'm now storing up here is 0. Steps to reach the tank, which is also 0, but that was from the previous solution. And then a flag for if I'm finding oxygen paths or not. So if the tank isn't found, and I'm not finding oxygen paths, or if the tank is found and I'm not finding it, so that's kind of like an implicit state there. I should be using something that's like initiate oxygen finding or something like that, and then flip it to a new state. But I don't do that. I just use a couple of booleans like a true programmer. So first, I go ahead and grab my current path, -1, which is going to be the answer to part 1. That's the length from the origin to the oxygen tank. Then I'm going to set my origin to the oxygen tank's position, and then reset paths and dead ends. Set the probe state to none, so make it pathfind again, and then tell it like, okay, now you are finding oxygen paths. So it basically will ignore this after this point, because tank found will be true, and this will be true. Then from there, I just have a simple addition to my pathfinding code. So if I'm, again, at an intersection or at a dead end of 3 walls, and my position is not the origin, so not the tank position, all this other code is the same, but now I'm going to check if the length of the current path is bigger than the longest path length. If it is, go ahead and store that new length. And then just basically keep pathfinding until I hit the origin, at which point I return. So down here, another addition that I add is say, okay, if I'm backtracking, so like I've basically I'm going to hit the longest path, and then it's going to backtrack all the way back to the origin, and that will be the, it should be, the last backtracking part, the last dead end that it finds. It will then backtrack to the origin. If it hits the origin, or if there's no path left, because I've removed them all and add them all to dead ends, just return, and that will stop the code program, and that will let these print statements run at the end. So if we want to run that, we can. It's going to take a minute to actually do all this work. So first, it's going to do the same thing it did before, which is go from the origin and re-find the oxygen tank. So there it hit a dead end. Now it's going to go further up to the top left until it finds that tank. And there it found it. And now it's going to start pathfinding to each dead end. And then when it finds the dead end, it's going to add that path to dead ends. So here you can see it's walking basically all the way back to the origin of 0, 0. So that's kind of inefficient because we already knew that distance, but not a big deal. It was easier to just wait a few seconds than to add that optimization in. So now I'm going to pathfind the rest of the maze. You can see we skipped the middle there. We're actually going to fill out the bottom first based on my up, down, left, right command. So I skipped another little hole there. And I thought about adding like down here the greatest path length as this was printing, but I don't know. I'm already behind on advent of code, so I kind of wanted to speed this along and just get it done. Even though I really like this puzzle because it's super cool and I really enjoy printing stuff to the terminal. So here you can see I think my furthest location is going to be down here somewhere. Now this is going to run a lot faster because backtracking means I don't have to find walls. Kind of reminds me of Pac-Man a little bit. There's a little spot. Now I'm going to fill out that middle because it skipped that before. Now we're going to zip all the way back to the origin. There we go. So this is the entire maze for day 15. And the greatest distance to a dead end from the tank is 358. So if we look back at our code, there it is, 358. And that's it for this one. Super cool to be able to do this and say like, okay, I started here. Here's the tank, and I wrote an algorithm that solved a maze. Like, that's kind of really cool. What this is kind of means is that like I've got code that if I had a maze that I wrote myself, I've got an algorithm that would like pathfind through that, which is pretty dang neat, in my opinion. I didn't expect to be able to do that with code, especially with Python. After doing advent of code for 17 days now. So making a lot of progress in learning Python, getting used to using sets and lists and all that sort of thing, which is nice. As far as my overall progress is going, I've got the first part of day 16 done. 16.2 is pretty tough, so I'm getting a little bit of help from some people that I'm talking to about advent of code, and like they already said that it's kind of like insane. So hopefully I'll be doing a video about that one soon when I solve part 2. But yeah, advent of code is it's tough to keep up with this with all the holidays and everything coming, and doing everything with family and all that good stuff. So these stay up all year. If you're not able to keep up, don't sweat it. Keep looking at them. Keep trying them. They're really good exercises, even though the instructions can kind of be hit or miss per day. Today was not really an algorithm problem. I mean, it was because it's pathfinding, but it wasn't really a data structure thing or a math thing. It was just a find a position in a 2D plane. So high school math or middle school math kind of problem, which is good because it's accessible to a lot of people. Some of the days like 16 are not that. It is very much a like SAT question kind of thing, which is pretty rough. So yeah, check out day 16 when I get that up, and keep going at home. Like, subscribe, comment, all that good stuff. Follow us on Twitter at TechJR Podcast, and I will see you for day 16.